Very good. So let's make a 2-minute summary of what we have seen yesterday. It was a very important day because we talked about modeling all the time yesterday. So of course, I'm going to share the screen.
Mhm.
All right. And okay, so yesterday was this presentation. And just to clarify, for chemicals that are not reactive, so for traditional simulation of pollution, and by traditional I mean the most of the criteria pollutant, the one that are like SO2, sulfur dioxide, or CO, carbon monoxide. For these pollutants, the Gaussian formula is ideal because it works and it is relatively simple. So the Gaussian formula is what I show you today for the Gaussian plume model, in which we have a bi-Gaussian distribution, both in the horizontal and the vertical. The Gaussian model has limitation, but it works quite well. And this is the basic formula. Of course, if you look at the manual, the user's manual of AirMod, this is the basic formula, but then there are 50, 60, 70 additional formulas that are used to add particular phenomena about ground reflection, deposition, and so on. But basically, this is the formula. And as you can see, is an explicit formula. Is concentration equal blah, blah, blah. So it doesn't require numerical integration. It doesn't have derivatives or integral or complex mathematical function. Is a simple formula, concentration equal blah, all these terms. So the simplicity of the Gaussian model is very appealing. And if we want to do something more complex, still maintaining the simplicity of the Gaussian model, we have the Gaussian path model, which is a very substantial improvement of the Gaussian plume model, theoretically. In practice, however, is not that has not shown yet superior results. And by the way, now all the links work because yesterday my envirocomp.com was down, and now I fixed it. And so all the link works. For example, if you want to see a full chapter on Gaussian plume model, there is this chapter 7 of one of my books that is showing the Gaussian model and the Gaussian plume model, MPAF. So all the links now work. Also, there is this other chapter from this other book. Here we are.
Hello.
Hello, can you hear? Oh, hello, Mirfat. How you doing?
Good.
Very good. Thanks for joining us.
Alhamdulillah.
I'm still making a summary of what we did yesterday. So, and I hope everything was clear yesterday. And I'm also pointing out that now all the link work with APSI, with EnviroComp. So I send you all the material shown so far yesterday via Hightail to both of you. So I hope you received it. And I hope you will start soon playing with screen view, as I recommended yesterday. Okay, so I was making a summary of what we discussed yesterday, the Gaussian plume model with this simple basic equation, and the Gaussian puff model, which is a major improvement with respect to the plume model, but is still relatively conceptually simple. And then we started talking about grid models. Grid models are much, much more complex because they solve the partial differential equation, the Navier-Stokes equations, for transport and diffusion of pollutants, and also they can include all the chemistry. So yesterday we stopped here, modeling of chemical photochemical reactions. This is very important, especially to simulate ozone, which is the most important product of photochemical reactions. Ozone is still a challenge all over the world. Other pollutants like SO2, lead, carbon monoxide, other pollutants have been reduced a lot, especially in the Western country, North America and Europe. But a chemical that remains a serious problem for air pollution is ozone. And ozone is just a typical example of a component of the photochemical smog. There are hundreds of components created by the photochemical smog, but ozone is the typical one that when we measure and we see high level of ozone, that means in general that we have problems with photochemical smog. And I already show you on the first day of my course, I believe, this simple visualization of how difficult it is to treat ozone. You may spend billions of dollars reducing emission of NOx in your city, and you do not achieve a decrease of ozone. Actually, you may achieve the opposite in this situation. And if you are in this situation, you spend billions of dollars to reduce VOC emissions, hydrocarbons, and nothing changes. The ozone remain more or less the same, because in this area, which we call NOx limited, the ozone isoplates are flat. So it's a non-linear challenge that is difficult to assess. I have several sets of slides here that I will go through, skipping a lot of material that, of course, you can examine on your own, just trying to identify the most important issues. For example, okay, these are the damage of ozone to the respiratory system. I've shown you this picture several times before. 1943 was the first big smog event in Los Angeles. People thought it was a toxic poison gases bombed by the Japanese. Instead, it was the first example of photochemical smog. And again, remember, ozone is good in the stratosphere. The ozone layer is protecting us from harmful ultraviolet solar radiation. So the bad ultraviolet radiation is absorbed here 20, 30 kilometers above the ground and doesn't reach us at the ground level. Very, very important. But at ground level, in the first kilometer of the atmosphere where we live, so-called tropospheric ozone is smog, is dangerous. So stratospheric ozone, good. tropospheric ozone bed. Ozone is a secondary pollutant. We cannot point a finger at anybody emitting ozone. People are emitting, we are emitting primary pollutants that are the precursor for ozone. And these primary pollutants are NOx and VOC, hydrocarbons. So these are the precursor. And then these two precursors in the atmosphere, they cook with solar radiation and they create ozone and many, many other photochemical pollutants. These are the basic formula, very simplified, for the chemical reaction that produce ozone. We knew this formula long time ago. The challenge was only to understand the oxidation of N. We knew that we were emitting NO because every time you burn something, you emit NO. Why? Because the air is made of nitrogen and oxygen. So whenever you burn something, even at your home, natural gas, or if you light a match, you are burning air. Burning air means creating NO, nitrogen oxide. So any combustion process, when they say this combustion process is clean, they are not telling the truth. Any combustion process in the atmosphere will burn air and will create NO. So we knew about emission of NO. We knew long time ago that if there is NO2 plus sunlight, the sunlight may be powerful enough to split the molecule of NO2 into NO plus O. O is very unstable, will react with oxygen, and it will create ozone. And also we knew that at nighttime, especially at nighttime, the emission of NO destroy ozone, recreating NO2. So we knew all this. The only big problem that it took us a long time until 1953 to understand was this formula. Why do we have so much NO2 in the atmosphere? We emit mostly NO. A little bit of NO2, yes, but mostly NO. Why do we have so much NO2 that is capable of creating so much ozone? This was the big question. And this was understood only when we realized the important role of VOC, volatile organic compounds, practically reactive hydrocarbons, chemicals that facilitate the formation of from NO to NO2. So this was the turning point. Of course, if you look into a photochemical model, you will find 50, 100, 200 equations, chemical reaction. But the structure of this chemical reaction is mostly simplified in this slide. So this is what's happening. Anthropogenic emission of NO, formation of NO2, cooking with VOC under the sunlight, and formation of photochemical smog. And as I show you before, in the Los Angeles basin, pollution is trapped by an inversion layer that keeps all the pollution inside the atmospheric boundary layer. There is a sea breeze moving the pollutants slowly from the ocean to downtown Los Angeles, to Pasadena, Azusa, Riverside. So we have different peaks of ozone at different time. This more or less is the scenario. Sunrise, emission of an OMVOC, formation of NO2, formation of ozone, sunset, and the next day, everything restart. Everything restart. And we have multi-day pollution episodes that historically have been very, very bad in Los Angeles. Now is better, but still we are above the standards. And again, we find these problems of photochemical smog all over the world, mostly because of transportation, because of automobiles. So in the western basin of Los Angeles, typically we have the peak of ozone earlier, maybe around noon. But the more you move east, the peaks of ozone are in the late afternoon in the eastern basin of Los Angeles basin. That's what we have found. And everything makes sense. Okay. And of course, in the last 50 years, everything has been managed by the South Coast Air Quality Management District in Los Angeles, one of the most famous air quality district in the United States, and I would say in the world. You can spend some time looking at their website. There is a lot of information there, historical information, and it's amazing what they have done in the last 50 years with a huge budget. So all this has been done with enormous expenses, but no, we have achieved some good results. This other set of slides, starting from slide 11. This is more complex. I'm going to show you only a few slides, but you will find a lot of additional information if you are interested in photochemical smog in this presentation that I borrowed from Dr. Christian Seigneur, a French scientist who have studied air pollution all his life. He retired recently, and he shared with me his slides. So again, photochemical smog is smoke plus fog. We call it photochemical smog or Los Angeles smog to distinguish it from the famous London smog of the 1950s that was completely different. It was a SO2 and particulate and soot smog. London smog was a winter smog. Photochemical smog typically is a summer smog and requires solar radiation. That is an ingredient. Without strong solar radiation, you do not have photochemical smog. So the chemistry is quite different daytime and nighttime. Daytime, we have photolysis. So we have reaction of chemical with light. Nighttime, of course, we have no photolysis, but we have other reactions that are important. In daytime, we have formation of ozone. Nighttime, we have destruction of ozone. What happened in the stratosphere? We have very strong ultraviolet solar radiation that split the molecule of oxygen in two atoms of oxygen. And of course, this atom will react with O2 to create ozone. So in the stratosphere, we have this ultraviolet radiation that create this good ozone that protects us from ultraviolet solar radiation at ground level. In the troposphere, the solar radiation, fortunately, is too weak now to do this. Everything has been done in the stratosphere. But now there is still, of course, solar radiation, and is not strong enough to split O2, but it is strong enough to split NO2. And then we have the photochemical smog. So these are the two different mechanisms for formation of ozone in the stratosphere and in the troposphere. Okay. Again, let's repeat. The key ingredient for photochemical smog are NOx, VOC, and sun, solar radiation. And then you create ozone. I think, and of course, at nighttime, we continue to have emission of NO because we continue to drive car, we continue to have industrial emission, we continue to have combustion. So at nighttime, most of the ozone created in daytime is destroyed by NO. This is a very important reaction. But next morning, the daily cycle restarts. Okay, yeah, here there are all the details of this chemical reaction and the role of all these intermediate chemicals that facilitate the oxidation of NO into NO2, which, as I discussed before, is critical for the formation of ozone. So this is all I wanted to tell you. And again, this is another image showing what I showed you before with those ozone isoplates. It's very important to know where is your city. Is your city in an area with high emission of NOx, or is your city in an area of low emission of NOx with respect to the emission of volatile organic compound? Because the strategies are different depending on the city you are. So that's why you need photochemical models to help you, to guide you before spending billions of dollars to improve the air quality in your city. You need some guidance on how to do it in a cost-effective manner. Sometimes politicians and bureaucrats just want to spend money and say, yeah, we are good, we spend money for the environment. Well, we are scientists and we have to say, yes, it's good to spend money for the environment, but it has to be spent in a cost-effective manner. Otherwise, you may get nothing or may get even results that are opposite to what you try to achieve. That's the main reason why photochemical smog are essential for urban planning. So there are different strategies for reducing what? The ozone precursors. I cannot reduce emission of ozone because there are no emissions of ozone. I can only try to reduce in a cost-effective manner the ozone precursors, NOx and VOC. Here there is a section on Paris, because of course the author of this section is French. So it's quite interesting. Even Paris, in spite of the higher latitude, is affected by photochemical smog. Very good. For completeness, I want to tell you that the first key paper why my link does not work. Okay, let's try again. So this was the first paper by Hagen-Smith, 1953, explaining the Los Angeles smog. Many people didn't believe him at the time, that both NOx and VOC were the key components, but of course he was right, and science have changed since the publication of this paper. Okay, so if your challenge in the future is to understand the photochemical smog in your area, in your city, in your region, what do you do? Well, many models were developed, but only two, I would say, have remained valid today to use. They are complex, they are difficult to use, they require a lot of work for learning how to use them. My recommendation at the beginning is always to use consultants to help you at the beginning, but you decide. There is the CMAC software developed by the EPA, so free of charge, fully documented, fully tested, and I probably have to go in presentation mode. I may have to go in presentation mode. Okay. Let me close this and restart. Okay, you see my my screen now?
Yes.
Very
Yes.
good. Very good. So let's go back. Which time is it? 6:34. Let's go back. We were talking about available photochemical model. I mentioned CMAC by the EPA, and I click, okay, now it works. All right. So there is a section in the Scrum site of the US Environmental Protection Agency, talking about photochemical air quality modeling. And basically, there is a lot of software available, but the two main software are the CMAC, developed by the EPA, the Community Multi-Scale Air Quality Modeling System, extremely complex, very comprehensive. This model does practically everything you need to do for transport, diffusion, deposition, chemical reactions. I really encourage you to spend an hour reading about this model, because this is the, as they say in the United States, this is the Cadillac of photochemical models, and it's constant evolution. They have a big budget, and they continue to improve this model. It's not just a model, it's a suite of models. And then the other model, that's the one that I recommend, because it's simpler, easier to use, and I think that's the best way to start to do photochemical modeling is with CAMEX. CAMEX was developed by a consulting group, supported, of course, by the EPA. Again, is free. You can download it free of charge. Is fully documented, and it's a very good software to simulate gas and particulate air pollution at the local scale, like an urban area, 100 by 100 kilometer, or a continental scale, like the northern US, Northern America. There are many publications available. There is an overview presentation here. Now the model is managed by Rambo. Rambo consulting company purchased the original corporation that developed CAMEX, and so everything now is managed by Rambo, which is a very large engineering and environmental consulting company. You have here a full set of slides talking about CAMEX. So my recommendation, if you want to start doing photochemical modeling, is CAMEX, at least to start. It's still difficult to use. My recommendation is to be guided by some consultant if you start, but it is the best choice. Okay, so how about deposition modeling? All the models we have discussed so far contain inside some deposition routines. So again, the work is done by the model. You don't have to worry about it, but you have to have a basic understanding of what you're talking about. Any pollution in the atmosphere will be affected by transport, diffusion, and deposition and chemistry. Deposition is the way the atmosphere cleans itself. The chemical eventually will be dropped to the ground or to the water. And deposition can be dry, not affected by precipitation, or wet, affected by precipitation. So all the models contain some routine. Some models have simple routines. Some other models have very complex routines. But all the models contain routines for simulating the removal of pollution from the atmosphere due to deposition. There are simple formulas like a decrease of 1% per hour. Very simple. Every hour, I reduce the concentration by 1% because it disappears. And other complex formulation. There is chapter 11 here from one set of slides, again prepared by Dr. Christian Seigneur, that gives all the details about transfer or pollutants between the atmosphere and land or water surfaces. So all the details are here, but again, you don't really need them because the model will do the calculation for you. And also there is in APSI, you will find one guide on the deposition phenomena with an explanation of what the way these formulas work with this schematic diagram and some information. There is this chapter. This is this full chapter on deposition, chapter 13 of one of my books, describing all the deposition formulas that you can use in your models. So a lot of material if you have particular interest in these formulations. But the concept is very simple. You have emission of pollutants, and a fraction of these pollutants eventually will go to the ground. And to calculate the concentrations, you need to know which fraction has disappeared. I think this is a good point to stop. So this was the most important part of my course, dispersion modeling with Gaussian formulas and photochemical modeling with grid models. I think I gave you a basic introduction, and I hope everything was clear, and the rest of the course will deal with the additional issues, but the most important part of the course was dispersion, deposition, and chemical modeling. So I hope it's clear. If there are questions, we have a couple of minutes now.
I don't have questions, Paolo.
Very good. Then I'll see you in 15 minutes.
Okay, perfect.
Bye.
Thank you.
All right. So now that I have finished the most important part of the course, Gaussian models and photochemicals model, I have to make decision. As I told you since the very beginning, I have a lot of material to talk for a month, but we have the last day today. So if you have any suggestion on topics that you are particularly interested, let me know. Otherwise, I will make the choice of what to present today. Very good. So let's go back to the first day material. I stopped here when we talked about the brief history of air pollution, and there are a few slides that may be of interest to you. First of all, a reminder of what the criteria pollutant are. Criteria pollutant are those that are used to be the most important in the 70s when we focus our attention on specific chemical that were of interest for air pollution, and they were ozone, particulate matter, carbon monoxide, lead, sulfur dioxide, and nitrogen dioxide. These are still called criteria pollutant because we started our air pollution studies with this chemical, and now, of course, we have many more that we are interested in. So these are the criteria. Then there are the hazardous air pollutants and air toxics. Hazardous air pollutants are defined. They include toxic, of course, but they also include pollutants that may cause explosion, for example, or damage to the environment, not to necessarily to human health. So in this section of the EPA, you find more information on what we define as hazardous air pollutants they are dangerous for several reasons. In particular, California has been the state always most advanced for studying air pollution, and in particular for studying air toxics. California implemented regulations and laws to control air toxics before the EPA, before this was done at a federal level. So they were always ahead of other states and even ahead of the federal government. So if you're interested in air toxics, I suggest you look at the EPA sites, but also at the California Air Resources Board site. California has formally identified 200 substances and groups of substances as toxic air chemical. So it's a lot. It's a lot. Here is the most important one. Benzene, of course, one of the most important toxic air pollutants. Hexavalent chromium, probably one of the most toxic air pollutants. I've done a lot of studies on hexavalent chromium, including, I want to show you because I'm very proud of the work we did in this case. So I'm going to open. I'm going to open my company, and I did a big chromium-6 dispersion modeling in Iraq. It is summarized here, the overview of the project. I didn't visit Iraq at the time, but I lived 2 years in Kuwait, so I'm familiar with that area. And if you're interested to know what we did for chromium-6 in Iraq, you can download my article. My client let me publish an article, a dispersion modeling of particulate matter containing hexavalent chromium during high winds in southern Iraq. So if you're interested, you can examine my work. Going back to California list of main toxic pollutant, asbestos, of course, all the metals, for example, cadmium, ethylene oxide, another important toxic pollutant. This is used to sterilize objects and tools in hospitals. So it is a toxic pollutant. Arsenic, of course, vinyl chloride, and other famous toxic pollutants. Formaldehyde, it is used on wood for preservation of wood. but of course then can be released from wood into an indoor environment. Lead, diesel, particulate emission from diesel. I already told you how important they are in terms of being the main reason of toxic contamination of the atmosphere. And finally, last but not least, environmental tobacco smoke. That is the smoke of cigarette that smokers force you to inhale when you happen to be near smokers. Things have improved a lot, especially in Western country, but also in developing world. Whenever I travel, I notice that is becoming more and more rare to be affected by cigarettes and cigar smokes indoor. Of course, people still smoke outdoor and sometimes can be extremely unpleasant, especially if you eat outside. So again, my recommendation, try to stay away from smokers because secondary tobacco smoke is dangerous and annoying. So this is just a small list of the main air toxics, but again, is more than 200 just in for the California regulations. Okay, emission of air pollution. A brief review of what are the emission of air pollutants. There are industrial emission. There is transportation. There are several sources of emission, including natural emission, dust storms, volcanoes eruptions, and so on. One of the main sources of pollution is combustion. Whenever there is combustion, you have as a minimum the generation of NO because of nitrogen and oxygen inside the air. I have a lecture 6 here that I can go through quickly. I already showed you these slides before. So let's give you some terminology. There are stationary sources that are fixed in space like a stack. And there are mobile sources that move in space like automobiles. First important definition. The main emission processes are combustion, fugitive, something that is just, how can I define fugitive? Something that happens not from a stack, but from an area source or a volume source, a combination of leaks, like in a refinery. These are fugitive emissions. Evaporative, you have a pool of hydrocarbons, it will evaporate. Or when you fill up gasoline in your car, you remember, you smell something not very pleasant. That is evaporative emission of gasoline at the time you pump gasoline in your car. Dust, emission of dust from wind or from a truck driving on the street and resuspending dust, and wildfire. Every time you have a forest burning, you have a lot of emission of chemicals. So any burning is polluting. In particular, if you burn a dirty fuel that contains sulfur, you will burn the fuel and the sulfur will be emitted in the atmosphere as SO2. And also there is always incomplete burning. whatever you burn, it will never be 100%. So there will be unburned fuel that will be injected into the atmosphere.
Paolo,
Yeah.
any burning it's polluted?
Say it again.
You say any burning make pollution?
Yes.
Even the candle, even the smell candle make
Any burning in the atmosphere, of course, with oxygen. With in the atmosphere, there is nitrogen and oxide and nitrogen and oxidant. And when you burn in the atmosphere, and N and O will react to create NO, nitrogen oxide. So that's unavoidable when you burn in the atmosphere. And then if you burn without oxygen, which happens sometimes, but in normal conditions, you burn in the atmosphere, as a minimum, you have NO. And as a maximum, if the fuel contains metals or sulfur or other stuff, these trace chemicals inside the fuel will not burn, but will create other chemicals.
Yes.
So, for example, if you burn wood, you will smell. You will smell when you burn wood. What do you smell? Sometimes it's a nice smell, but it is hydrocarbons. It is pollution. When you burn coal, you smell something. There will be coal particles that you will smell. So it's impossible to have a perfect 100% combustion. So even if the fuel that you're using is clean, like natural gas, people always say you burn natural gas is clean, is non-pollutant. Well, yes and no. Every time you burn something, you have NO. Burning is our civilization started with fire and cooking meat, but there is a price to pay. The price is pollution. Okay, since you asked this question, let's elaborate a little. This is a typical basic chemical reaction when you burn an hydrocarbon. Hydrocarbon, HC. So you burn an hydrocarbon and air is involved in the chemical reaction. Air is N2 and O2, nitrogen and oxygen. The main product, what are the main products of this combustion? Well, first of all, energy. That's why you burn stuff, to create energy. But what are the other products? CO2, which is not a pollutant in terms of human health, is an inert gas, actually is a plant nutrient, CO2, very beneficial to vegetation. H2O, water, is not a pollutant, and other products. What are these other products? Carbon monoxide, because in complete combustion, not all the carbon C end up in CO2. Some of the carbon ends up in CO, and that is a pollutant. SO2 if there is some sulfur inside this hydrocarbon that you burn. NOx for sure, unavoidable. You burn hydrocarbon in air, you will create NOx, particulate, and so on. So these are the basic chemical reactions of a combustion of hydrocarbons. Ideally, you would like only to produce energy, CO2, H2O, ideally. But unfortunately, that's not the real world. Yeah, if you have a perfect complete combustion, you should generate only CO2 and water vapor. Fugitives. This is an example of fugitives. You pump oil and you have vapor coming from your well. You have an industrial facility and you have leaks from the roof. These are all examples of fugitive emission. You pump gasoline in your car, or you have paint in your home, and when you paint, you have evaporative emissions. Dust. Every time you have construction, Paula, you mentioned construction activity in Malta a while ago, and certainly every time you have construction, you have dust. The best way is to add water constantly to minimize the emission of dust, but sometimes it's difficult. Wind-blown dust event in Phoenix, Arizona. This is an example. I lived 2 years in Kuwait. I remember a few dust storms over there. Quite amazing, those dust storms. So you, all of a sudden, you are surrounded by dust. And even if you close the window, the dust is so fine that will enter your house through, even with closed windows. Wildfires, natural or man-made, are extremely important. I used to live in the San Francisco Bay Area. I've lived here for 30 years. And now I moved to Reno, Nevada, which is here. If you see my mouse here, actually. And sometimes we have a lot of smoke coming from fires in Arizona. So the smoke is strong enough to affect California and even Nevada. Internal combustion. Okay, I already talked about this. The perfect combustion and the real combustion. And let me tell you, this a great success story in terms of car emissions from the 50s to the 90s. We had reduction of hydrocarbons from 13 grams per mile to 0.25, 2 orders of magnitude. Reduction of NOx from 3.6 grams per mile to 0.4, 1 order of magnitude. Reduction of carbon monoxide from 85 grams per mile to 3.4 grams per mile. So the improvement in emission reductions in automobiles, first in California, then in the United States, and then all over the world, has been enormous, enormous. 1 or 2 order of magnitude. You can imagine how bad things were in the 50s and even the 60s with this type of emissions. But of course, in the 50s and the 60s, we had less cars. So we have a great improvement in emission of the average car, but also we have an enormous increase in the number of cars. So the improvement in air quality has not been as big as we could have expected because of number of cars and number of drivers. In fact, I have a graph here. Now it's another presentation. I'll show you later. Basically, the improvement in car emission were achieved through federal government rules and standard, but especially new emission control technology developed by the auto industry. They really made enormous progress from the 50s to the 90s in reducing the emission of chemicals from a typical passenger car and also from trucks. This is undeniable. If you are interested, there is a presentation here discussing all the details of the refueling system, of what has been done to minimize the evaporation of gasoline when you pump gasoline. So I don't know in Malta or in Saudi Arabia if you have this type of technology. Even the United States is not everywhere. It is in California, but in other areas is not installed. But major progress have been done in minimizing the evaporative emission of hydrocarbon when you pump gas in your car. And if you're interested, this presentation here will give you a lot of details on this technology and the improvement it has generated. For example, these are some of the improvements. To show you how air toxics are everywhere, and you have to be very careful, especially if to minimize your exposure. It's not just a major emission from the industry or from the traffic in a highway. Even small operation can expose you to air toxics. For example, when you pump gas in your car, as I told you before, you smell it. There is some smell, and there is gasoline that may be remain in your hands, and you smell your hands. Those are toxic pollutants. Small amount, but they are toxic. Also, dry cleaning operation. I don't know if you remember now, dry cleaning operation have improved, but if I remember entering a dry cleaning shop 20 years ago, I immediately noticed some strange feeling of the air pollution inside. And this was due to perchloroethylene, a toxic air pollutant that we have studied in the last few decades. And there is a full section here on the EPA site on how to reduce emission of air pollution in dry cleaning shops. Perchloroethylene is really one of the major air pollutants that are used for dry cleaning, and but not anymore. Now, many dry cleaning operations have a sign, no perc. No perc means they are not using perchloroethylene. So they put a sign in front of a door to make sure that the customer know that that their shop is clean. And I could do other example. Toxic air pollutants are everywhere. When you clean your home, you smell something. Chlorine based material. Those are toxics. Short-term exposure are not going to be a problem. But if you work in an environment that always have cleaning operation or like chlorine, you may have, there is some danger. Every time you are exposed to toxic pollutant, secondary tobacco smoke, smokers, cleaning, heating. If you have a wood stove in your car, in your home, or a fireplace, and you burn wood, and you like the smell of the wood, but again, All these are toxic pollutants that you should minimize exposure to. Of course, there are natural emissions also that you have to be careful. For example, radon. Radon is a radioactive gas that is found in rocks and underground surfaces. And this radioactive gas can penetrate your home from the basement. So it is possible in certain areas you build a home, and then you measure radon inside your home, and you find that there is some amount of radioactive gas. And as you know, radioactive exposure is never good. Even a simple X-ray, anytime you have X-ray at your dentist or other doctor, is radioactive exposure. So a minimum amount, but is non-zero radioactivity that you are exposed to. So there is always a danger when you are exposed to radioactive gases or you inhale radioactive gases. Let's see what we have here. Yeah, this is a nice summary paper. Well, is an article, actually, not a paper. It's a nice summary to explain the difference between human, anthropogenic, and natural air pollution. It's easy to understand. Anthropogenic emission, let's make a list. We have the main anthropogenic emission are fuel combustion from motor vehicles, heat and power generation, power plants, oilers, industrial facilities, mines, refineries, chemicals, manufacturing, waste sites, and waste incineration burning. And last but not least, especially in developing country, this is extremely important. Most of the air pollution, even though people sometimes don't realize that, but the most dangerous air pollution on Earth is in developing country, where they have primitive residential cooking, heating, and lighting with polluting fuels. You know, many places around the world, if you go to Africa, Central America, some Asia, they really use the cheap, dirty fuel to cook, to heat, and to light their homes. And these fuels are used indoor. So that's what makes it very dangerous. So indoor air pollution is much worse than outdoor air pollution, especially in the developing countries, because they use cheap, dirty fuels, and the emissions are strong. The emissions are toxics. The emissions are indoor, and they remain contained indoor. And people, don't forget, people spend 90% of their time indoor, their homes, their work. So the exposure is strong and long. So this is really still a big problem, especially in developing countries. The first challenge for developing countries should be to bring them clean natural gas to burn, to cook and to heat, and drinking water. I believe that anything else should be second priority. First priority for all over the earth should be to assure that everybody has clean natural gas and drinking water. With these two, when these two problems are solved, around the world, in my opinion, things will be much, much better. And then we can start worrying about other things. That's my personal opinion. Some more discussion about emission, industrial activities. I have a pointer here that you can examine if you're interested. What is an industry? From small to big, how do they interact? How can be categorized, heavy, light, domestic, foreign? You have all sort of important definition. Transportation, that's really the key. 100 years ago, air pollution was due to industry, practically. Today is mostly due to transportation. And transportation, we have light-duty vehicle, our automobiles, heavy-duty vehicles, trucks, motorcycle, sometimes small motorcycle. The scooters are the worst in terms of air pollution. Is unbelievable. Some scooter emit 100 times more than an automobile in terms of pollution, especially in terms of toxic air pollutants. It's amazing. Sometimes you travel to cities in developing countries, and the real air quality problem is motorcycle and small scooters. And then what else? In non-road emission, airplane, diesel equipment, construction equipment, ocean vessel, train, locomotives, garden machinery. And when you take care of your garden, you have machinery that are quite pollutants. You can smell them far away. And recreational vehicles for boats and other recreational vehicles. All these sources of transportation, of air pollution for transportation, may be improved. And I'm not going to go through the list, but only mention the catalytic converter that has been really, the catalytic converter has been the key for improving air pollution in cities and reduce emission from automobile, really the key. But again, with money, of course, because reduction of air pollution requires money, and each of these sources may have reductions with good investment in this technology. There is technology to reduce the emission. It is expensive, and don't forget, we should always do cost-effective things. If something is very expensive and has little reduction of air pollution, we should wait and focus our investment on technology that is very cost-effective and reduce air pollution in a way that, you don't need a big budget. So it's not enough to do modeling of air pollution. You have to do also cost strategy, risk optimization, optimization in general of resources. Very important. Sometimes people jump into establishing a budget, spending money, and then 10 years later you realize that you could have spent half and have much better improvements. So we scientists should always push for the application of the best available science and the best optimization strategies. In other words, we want objective decision, not subjective. Sometimes politicians and bureaucrats, they want to do what they want to do based on subjective opinion. We scientists should always push for objective solutions based on best available science. I mentioned to you before the AP42. Let me repeat. AP42 is thousands of pages of document covering virtually every type of emission: combustion, solid waste, evaporation, petroleum industry, chemical industry, storage tanks, agricultural industries, wood product, metal industry, and so on. You will find some guidance, initial guidance, to calculate emission rate for any type of industry in a P42 document by the EPA. Very useful first start. Okay, so this is what I didn't finish on the first day that I wanted to finish. We have about 5 minutes before the guest lecture of Dr. Jacques Musafir on street canyon air pollution, urban air pollution. We have time for a few questions or comments if you want.
No, thank you, Paolo.
Otherwise, I will use these 5 minutes to, there are a few slides in the day 2 presentation, which I didn't finish. Yeah, we were talking about regulatory modeling. Yeah, regulatory modeling is called the use of air models not for scientific reasons, for pure research or for academic reasons or to write a paper. The use of models to comply with regulations. In the United States, but now all over the world, if you want to install or construct a new industry, you need a permit. And the government will give you a permit only in most countries or in many countries, only if you satisfy some regulatory conditions of safety, of fire control, of all sort of conditions. Otherwise, they don't give you a permit. One of these conditions to get a permit, you need a permit for everything now, to build a house, to build an extra room in your home. And in particular, if you build something that will pollute, will have emissions like a new factory, a new plant, one of the conditions is that your emissions should not create concentration that exceed some predefined government standards. This is what regulatory modeling is: to apply models for the purpose of convincing the government and the agencies that you will not pollute more than a certain level. So it's complex because it has a lot of regulatory conditions. In other words, if I apply my model to write a paper on a journal, I decide which model to use and I decide how to use it. But if I run a model for regulatory purposes, I will have to follow guidelines. All the government, in particular in the United States, have very strong guidelines that tell you which model to use and how to use it. So Regulatory modeling is a science in itself. And for example, let me see if I can find it. Yes, appendix. In the United States, there is the famous appendix W, air quality. Let's see if I can find it. Yeah, here it is. This is the most recent 2023 Appendix W by the US EPA. Here they tell you everything you need to know. Is the guideline on air quality model, which is 43 pages of rule and guidelines and document of how to use models to comply with EPA regulations and what to do. So if you are not in the United States, and if you don't do regulatory modeling, there is no reason for you to examine this. But I think it's nice. It's nice sometimes to be able to say, I follow the guidelines of the Environmental Protection Agency in running this model. Even though you may be, for example, in Saudi Arabia, but if you do a regulatory modeling application, you may want to say, you may decide to follow guidelines of the United States or Canada or Europe or whatever. In addition, of course, to the local guidelines that you have in your own countries. So that's something that I wanted you to see, that for regulatory modeling, we have a lot of precise rules that you have to be aware of and you have to follow. And most of them make sense. Most of them make sense. Okay, so we finish here. Next presentation of Dr. Musafir, and then we have a final lecture by me, in which I will go back again to all my PowerPoint, and I will try to extract additional information to provide to you with the material I have. So I'll see you in 15 minutes. Okay, so this is the third seminar of this last day of our course, and it is my pleasure to introduce Dr. Jacques Musafir, a top scientist in atmospheric sciences, air pollution, and technology, and also a very good friend of mine since at least 35 years. And Jacques, we have two people today with us, Paula from Malta and Mirfat from Saudi Arabia. And you can start your presentation now. Thank you, Jacques.
Okay. Hello to everyone. I'm going down, going up to the original screen. Do you see my shared screen well?
Yes, yes, we can see it well.
Okay. So I just said to Paolo that I would focus on what my specialty is, that is the high resolution 3D building aware urban flow and dispersion modeling for cities, which is a bit a long title, but it tells that we are, of course, users of many regional and city scale systems, but we're specialized in high resolution. Nevertheless, I will also show an example of one of the best or most interesting systems we have made, because it shows how close the link can be between what you can do at regional scale and what you have to do at local scale. The coupling of the scales is probably the good keyword to have an efficient modeling system nowadays. You can really avoid you can't really avoid going from planet scale to street scale. It's a bit difficult, but that's the way it is. So here I have proposed a short resume of what I did. I'm 67. I'm the founder and chief executive officer of ARIA Technologies. I was in charge of significant R&D activities and in the field of microscale Lagrange and particle modeling or regional modeling. I'm still in charge of this, but I've been running this company for a little over 30 years now. And my background is fluid dynamics and a PhD in oceanography and meteorology from the Paris Université Pierre et Marie Curie University. They changed the name now. It's called the Paris Sorbonne, so it's better heard in the world. And I've been working initially in the field of remote sensing with the Doppler sonar systems for the French Electricity Board. And I worked also in emergency response system for 7 years with them. And it's in 1990 that I decided to create ARIA Technologies as a consulting company specialized in meteorology, air quality, and dispersion. And we then founded AriaNet in Italy in 2000 and ARIA do Brasil in Brazil in 2010. So I'm now mostly doing the management of relatively large-scale projects, and I'm especially responsible for the North and South America activities of ARIA, including the US DoD activities, as well as all the Gulf area. This is why I've noticed with interest that you come from Jeddah, so we'll probably show things that will be of interest to you. Now my company, ARIA Technology and AriaNet, the Italian subsidiary, they both joined the Suez Air and Climate Solutions division. So Suez is a very large 40,000 plus persons global company with a key interest in water treatment and waste management. And they are also relatively good in environment, and this is why they decided to add to their capabilities the know-how of ARIA and AriaNet. And it's very nice for us to have this partnership. Now, what do? We essentially do modeling of atmospheric emissions, meteorology, and air quality. Although we've been adding significant activity in climate change in the past 10 to 5 years. It was a real change for us because the need for serious climate change simulation came out. Our expertise, as written in the slideware, is mostly high resolution, high performance computing numerical simulations for emissions, meteorology, pollutant dispersion, and air quality. And I will talk a lot today about the AirCity high resolution urban simulation tool, and not today about the simulations of climate change effects, because this would lead us very far from our 45 minutes. As for reference are concerned, we work for governments at the regional or national scale. One of our key customers is the US Department of Defense, for work we do with LIDARs. We work for Tunisia, Romania, Chile, the Kingdom of Saudi Arabia, Israel as well, and many, many cities worldwide, and large industrial customers. So in practice, with these three groups, you have the main customers of my company, and on the side, you have some tentative sketches of drawings, what we do. This one is a little more detailed, but we may have a look at at it when Paolo transfers you the content of this presentation. It is just the 5 areas of expertise where we work. We also have a little renewables system, but in essence, we work for industry, for cities, for risk assessment, accidents, toxic risk, and climate change, and renewables marginally. But with time, you may read this boring description of everything we do. Today, I'm trying to transfer a message. This is the outline of what I will try to present today. I want to insist on the fact that urban modeling is a multi-scale problem of hierarchy of models. It's very tempting to separate the urban problem and say, okay, this is more scale. We're looking at streets, we're looking at the city. And so it is separated from the regional or long-range transport modeling. Well, unfortunately, this does not work. And I think that the example of Saudi Arabia will be very clear on that. Because if you look at the atmosphere of a large city, of course, it is influenced by the micro-scale emissions, by the emissions from cars and the high density maybe of the stacks in a given industrial area. But it is also influenced by the regional or continental scale deployment of particles. And since many things depend from the reactions between gases and particles, especially the secondary pollutants dynamics are linked to that. The only way to tackle properly the urban problem is to couple the 2 approaches, the regional one and the local one. So I will try to make that understandable. This is, I swear, one of the 2 most complex drawings or tables I will show. In essence, what is shown here is that we have a stream of meteorological analysis and forecast, which is trying to downscale from what is told us by the NOAA or ECMWF forecasts that in general have a spatial resolution of something like 50 kilometers, which are run by probably the best meteorologists in this world. And these are global meteorological models that run daily with a time horizon of maybe 7 to 10 days now, and an average resolution of about 50 kilometers. Of course, over Europe, ECMWF is making a little better, and the same for NOAA, who has models that go to higher resolution than the US. But let's take this as the order of magnitude of the resolution of those models. Then, since this is available for everyone and for free, what we have to do if we want to go down to the micro scale or to the urban scale, which is figured here by urban risk, we need the intermediation of a regional system. That is, we have to downscale the forecasts using a hierarchy of nested model. Nesting is try to represent it on this picture, showing a higher resolution domain nested into there's an even higher resolution domain nested inside. This is part of the Arabic-Persian Gulf with a zoom on the Strait of Hormuz, I think. And this is to show that we can have a much higher resolution wind field, and we can go down to scales that are of the order of 500 meters, and then to go down to the urban scale, that is with resolution as high as 5 meters, we need to introduce the obstacles And here we have a special CFD model, which is different in coordinates and in nature from the models like WRF and SWIFT. So this is what I call the meteorological stream. And I'll just ask a question because I don't want to talk in vain. You probably have already heard about WRF and maybe SWIFT during the presentations. This idea of having a flow, a stream of meteorological analysis and forecast. Is this something new to this audience, or are we all on the same page here?
We are all on the same page because we have seen it with Paolo during these days as well.
Okay.
Yes.
Fine. So now the second part, to go from planet to street, is to have a local dispersion system. So this is a prolongation of the previous graph, which I have called the local dispersion module or the local dispersion stream. And we start from the meteorological data that we have into the MET model and with WRF and the SWIFT model. And then we can enter to a higher resolution system. And for this, there's a variety of models that can be used, but I will mostly focus today at the micro scale on Lagrangian dispersion models, which is a common passion from Paolo and from myself since a number of years. I think I met Paolo when I was probably 25. He was giving a conference in Italy, and he was convincing everyone that Lagrangian dispersion was a key to have precise dispersion modeling. And so we have made a model together years ago. And from that model, we have derived a Lagrangian particle model called SPRAY. And it has a version called microspray, which is able to do the dispersion of particles, taking into account obstacles. And this is what we use to go down to street scale or building systems scale and to do high resolution urban modeling. So I hope I haven't been too boring, but I thought it was necessary to explain why to go down to the street scale, we have to start from the planet scale. Otherwise, we'll do just nice things, but not quite efficient in the end. And this is a kind of summary of how and why urban modeling is done. So it is a multi-scale problem. We need a hierarchy of models at all scales. The coupling between scales is essential. And now I will talk a little more about atmospheric emissions, because sometimes this is a subject which is a bit overseen. I don't know, probably not in this APM webinars, but I will tell a few things about the atmospheric emissions. And then I'm focusing here on the fact that urban planning decisions depend on modeling. That is, it's quite hard to take safe urban planning decisions about heat island effect, climate change mitigation, traffic impact reduction without a good model. This is why we believe a lot in modeling as an essential tool. Monitoring is essential also because it helps and it's necessary to validate the model hypothesis. But modeling is clearly the tool to pilot climate change adaptation as well as all details of urban planning. Now I will go to this atmospheric emission key point. It's a set of slideware where I'm trying to introduce some things that you've already seen. So it's clear that for industrial emissions, we need to use probably the US EPA recommended dispersion tool. You have heard certainly a lot about air mode and cut-off systems during these days, and we are no exception to that. Of course, the EPA corpus of model have been developed by many bright minds in the past 20 to 30 years, and it's not necessary to reinvent the wheel. And I believe that we are heavy users of them, essentially when they're linked with GIS systems, because they give the most efficient way to display the result. On the other hand, if you look at other and more complex emissions, there is a need to go beyond the purely stationary source of stack emissions, the ones that you have described in general for the industrial sources. We need to tackle the area sources, taking into account every kind of source. And also you have to work on mobile source emissions. So the emission inventory problem, when you look at the very large regional problems, is very different. You have to move to collect a large set of geographic data to mix all the possible emissions. And you also have the necessity very often to use a traffic model. The one that we know well and that we use is traffic. I just want to go through an example. There's in the US IVE, which is also a well-known traffic emission modeling system. It's necessary to have details on the mileage and speeds of the cars and all the vehicles, trucks, etc. Fleet composition, emission factors, for example, the EU Copert or other emission factors. And then you can construct both a set of line sources that give you the emission of every link and area sources that will give you the emission by area, averaging what you have in a more global way than looking at the very detail. This is the example for a study we did recently in Lagos for the World Bank, Lagos, Nigeria. We have been using a collection of over 140,000 links that were injected into the traffic model to determine the high resolution database for traffic emissions. And I don't know if you know Lagos, but it's a 25 million inhabitants city with a very impressive quantity of cars and relatively low respect of regulation. It's an oil country with a booming population. So the air quality issues in Lagos are very tough. So you can't analyze what's happening if you don't work on traffic emissions. Another example, this is an example not to forget the aircraft or airport emissions. Here is an example of what we did for the Napoli Capodichino International Airport, which is the 5th airport in Italy and medium-sized airport. Here you have to clearly do an analysis not only of the local emissions of the airport, but of the emissions from all the aircraft according to their routes. And what you see in this map is the nesting of domains to simulate the Naples area. and how to include the contribution of aircraft. Another example, just to recall the importance of emissions, this is an output of what we did for the government of Tunisia. And we made a complete modeling system, and in Tunisia and in Jordan. So we did as a cut and paste that comes from something I did for Qatar Energy. So I'm sorry for that, but the purpose is just to show how complex the creation of an emission inventory can be. On the map of Jordan that you have here, of course, there are various very large areas which are essentially desert, but the details of emissions for the city of Amman are quite important, and because they dominate the whole picture. So this is just what I wanted to say about atmospheric emissions, because in order to do some efficient modeling, you don't have to forget to focus on all the aspects of emissions and not only on stacks. This is probably, for me, one of the key points. And I will now move, if you don't have any urgent question, I will move to the description of the Saudi multi-scale regional to urban modeling platform that I wanted to introduce. Here, I'm insisting on the fact that nowadays it's kind of mandatory to make use of existing systems developed in the EU and by public laboratories in Europe and the USA. I think especially about NOAA data for meteorology and the Copernicus data products that come from the European Union. Copernicus is running a worldwide forecast of air quality daily, as do some agencies in the US. But in my opinion, the Copernicus data products now are quite efficient. In the map that you have here, you have a map of an extraction of the standard output for the whole Saudi Arabia Peninsula, and including the Red Sea, the Persian Gulf, and then the Indian Ocean below. It's clearly a very powerful tool, because in order to do modeling, you can consider that all what is at larger scale, and especially the boundary conditions, are given. You know, if you work in Saudi Arabia and you don't want to ignore that there is some stuff coming from Cairo, that there is some stuff coming from Sudan, that there is a lot of stuff coming from the Emirates, from Qatar, and from Iran, you just need to look at the large scale. And in order to look at the large scale, did my slide change? I don't hear anything, so is the connection still okay?
Yes, it is okay.
I'm sorry. So this is the presentation of what we did for the National Center for Environmental Compliance in Saudi Arabia. The center was initially located in Riyadh, but now it has another siège in Riyadh. So Jeddah and Riyadh are the two places where we're running. And we provide a continuous high-resolution real-time MET and air quality model for the whole kingdom. And we have created zooms on 6 cities with a high-resolution urban model, provide a continuous weather and air quality map. And here we delivered for 24/7 hourly 15 minutes weather and air quality forecast map with 48 hours forecast and with a focus on specific areas. So in the drawing that you see here, you have the air quality, the whole map of the region, and then you have the location of 4 zoom areas. And inside these 4 zoom areas, which are 4x4 kilometer resolution, you end up having a high resolution domain for 6 cities that I will show some detail of later. This is a nice view of myself in the middle, and this is the control room of the Saudi Arabia system, of the NCEC system, with the operators and the different people that contributed to the systems. And I hope this will be moving. Yes. Do you see it moving? Is it actualizing properly?
Yes.
So this is to, again, to stress the fact that air quality is a multi-scale problem. If you look at the whole Saudi Arabia, you can see that there are clearly sea breezes setting up along the various seas that surround it, the Red Sea and the Gulf and the Indian Ocean, and that this is giving a very complex wind field pattern. It's not very easy to speak of the wind direction over a country as large as Saudi and with as much thermal contrast between the sea and land. And this is just a standard WRF output. We just configured properly. No invention from our part. You can see that in the output of every good model. Now, this one is probably one of the most interesting. Initially, when you start doing an air pollution problem and you come from Europe, you say you will work on the usual suspects that are nitrogen oxide, SO2, etc. And then you realize that when you are in Saudi and in parts of the planet where there is a huge quantity of dust uptake, then the problem of PM, PM10 is as an other order of magnitude than the ones we normally observe in higher in the Northern Hemisphere, in the US or in Europe. And this beautiful graphic is a set of 3D ISO contours of PM10 concentration. And there is a, I'm sorry, there is a color scaling that shows you that the parts where you have the larger values in the reds are not located on cities, but are located in the drier parts of this continent, and where the dust uptake is higher. Now, if you remember that animation, we look at the situation for ozone, and this is exactly the same timing. You see, the picture is completely different because there are no emissions of ozone, as we all know. Nobody is emitting ozone. Ozone is purely created by the reaction of nitrogen oxide and volatile organic compounds in the vicinity of cities or industrial cities. And it's clear that there are not so many industrial cities in the center of Saudi. There is only dust uptake. On the contrary, there is a lot of industrial activities on the seashore, both on the Gulf, on the right-hand side of the picture, and along the Red Sea, close to Jeddah, precisely. And it's very clear that the ozone maxima here are produced by the existence of sources of precursors, and as a secondary pollutant, the locations where you have ozone are very different from the ones where you had PM. Nevertheless, if you want to understand what happens at high resolution in a city, you need to understand the large-scale problem also. This is another example of the emissions of NO2 over Saudi Arabia. This is NOx, I'm sorry, not NO2. And what I can show here is the fact that we have taken into account all the emissions, including the ones from the ships along the Red Sea. With the Suez Canal, and on the Gulf, you realize that both seas have a very high traffic of very large ships that are the oil tankers. And along the Red Sea, you have a huge traffic through the Suez Canal. So this is showing that you cannot ignore the emission from ships if you want to be serious on air quality in this type of situation. This is ozone, and it's quite different from the NO2 because in the places where you have strong emissions of nitrogen oxide, you have the ozone, which is basically killed. I'm sorry, I had a control problem. I'll try to go a little quicker. So this is just a summary of Saudi Arabia. Now let's go to high resolution, which is the key subject of this talk. And I'm left with about 10 minutes, so I'll try to go a little faster. And for each one of the cities, I will show essentially Jeddah here. We have done a high resolution simulation taking into account the emissions of each and every street. And this is useful to understand what happens for the creation of a new neighborhood, the extension of the tree cover, reduction of traffic emissions. And this is an animation. I hope it will start. Yes, it does. An animation, I hope you see it well, of a Google Earth, presentation of what happens in the city of Jeddah. And it's interesting to see the interest of a high resolution simulation. This one is probably made with 10 meters, where you can see the details of the emission at major crossroads, where we take into account the output of a traffic model, similar to the one we used in Lagos. And we're really able now, with the incredible growth of power of high-performance computers, to describe with some detail the spatial distribution of air pollution over a large city like Jeddah. Of course, the places where you have the interchange between highways are the worst place to live by. That's not a secret, but it's very clear on this animation. Now I have been showing what we have done in Saudi. I would like to maybe go to what we have to explain how the RCT solution works. The idea is that we want to be able to do down to 3D metric resolution for CFD for urban areas in real time. And we want to be able to do both analysis, forecast, and scenarios. And this is a kind of explanation in pictures. We want to be able to do the whole city, and you can see an animation of the, I think it's the NO2 map for the whole city, hour by hour. And we want to be able to do also detailed description of the distribution along the streets for each major square and across buildings. I will move to another, hoping that it works correctly. This is another way to show the same simulation. It's a video. And what we display at the ground level is the concentration in NOx at the breathing level, which of course is very much dependent on traffic. So here you see Arc de Triomphe. And what you can notice also is that there are avenues with more pollution than others, and also that you have the typical canyon effect where the distribution of pollution in different sides of the avenue is different. The bubbles here are the location of the measuring stations of the Air Quality Management Board of Paris, which is called Air Paris. And here you see that, of course, the gardens are a little protected, which is not the case for the places where many cars are constantly circulating. And apart from the fact that it's interesting to be able to do that, of course, the number of nodes of the computation of computational points is quite high. We have millions of nodes here, and it's run using HPC resources, which are getting cheaper and cheaper. This is obvious. And I won't spend too much time on Paris. You may have a look at the complete video another day. This is another way of showing the results with during these experiments in Paris, we also had cars equipped with microsensors that were traveling. So this is showing a car going through a pathway inside Paris, and it's represented over Google Earth. But in this particular case, there was not too much pollution, so it's only light green or yellow. So it's not the best one I can show. And I will show an example. This is what we did for Hong Kong. We applied the RCT system for Hong Kong for Renault Nissan to study the quality co-benefits of introducing electric vehicles in Hong Kong. Of course, now Renault is with many other big car makers completely moving into the electric cars business. Tesla was alone for some time, but now everybody's playing the game. And it's interesting that Renault was studying that about 10 years ago already. Now, for the SCT platform, we also have other users than the purely civilian ones. I wanted to go to another link, but I'm wondering where it is now. But, let me see. Do you see my screen now? Yes?
Yes, we
yes.
can see.
Okay, so I'm zooming hardly because this is an example of RCT, which I find very interesting because it shows simultaneously the wind and the concentration. So the little arrows, white arrows that you probably see, I hope you have enough resolution, are wind arrows. They're related to the wind direction. So you see that over the river, with this flow direction along the river, they're relatively uniform. Then you can see green to red concentration ISO contours. And I want to go a little farther here to a quite known place. This is the Louvre Palace. And here you see that even though the wind is very uniform over the Seine, you can see that here you have recirculations because the buildings are large enough to create a whirl.
Jacques, we don't see the last 30 seconds you talk with the Louvre is lost. So I think it's frozen the video right now.
Ah, okay. You don't see anything. It's black.
I see the Paris. There are two images, one on the left and one on the right, but I don't see wind vector.
Okay. So there is no sharing of. Okay, I have been called calling a website, and so it's not transferred to.
Maybe you need to move the window in another monitor.
I don't know. Okay.
Okay.
We'll skip that because if it doesn't work, it's a pity because you could see how the flow is really modified by the presence of the obstacles. But let's go a little beyond. There's another key applications of the RCT platform solution, which is what we call the accident urban simulations that can be applied for fires, for terrorist actions as it happens. So we have deployed this RCT particle model, and for example, it's applied in Kuwait by the Kuwait National Guard, and it's an operational system on which I won't give too much info, but it's enough to say that it's possible to do accident urban simulations with a city. Here you see something that is more open or public than the things we did for the Kuwait National Guard. This is an example of a simulation with 2 fires on ships in the Marseille area. And this is again a particle model. It's PMSS, the model inside Air City. And you can see that the influence of buildings is quite clear. Initially, the plume is very thick and narrow, and then when it breaks into the buildings, it creates channeling, additional horizontal dispersion, and relatively complex patterns. Same can be done for industrial sources, and this has been done in the whole area of Marseille. So we have taken all the plants, all the industrial plants, and they can turn on an alert for any incident, event, toxic release, fire that can occur in their area of control. So the previous slide was with fire from ships in Marseille, and this one is more from an industrial accident. Again, once you have technology that allows you to do urban dispersion. You can do it real time and also with emergency response system that can be deployed. And so we've been developing a tool that we have been calling ResCube, which is able to use the wind information, wind and turbulence information from Doppler LiDAR, which is a relatively small unit. You can put it on the back of a small truck, of a pickup truck actually, and you can go close to the site of an accident and have the scanning by LiDAR, by laser of the atmosphere that will give you the wind information, and then you can run a modeling and dispersion tool and taking into account the buildings, if you have the topology of the city, which is the case in this example, you know which are the streets that will be channeling or not your plume, and it's a clear help for the fire brigades. Same for the forest fires. We're developing, it's still not out yet, the solution to help the fire brigades that would have a unit that can be on a truck, or they could even load a LiDAR on a chopper and put it down at the ground upwind from the fire in order to have an idea of the detailed wind field, incoming wind field. Then this is another video, so I hope it runs. Do you see something?
Yeah.
Yes?
Yes.
Yes.
Do you see me?
Yeah.
No.
We see your video and we see your screen, something moving. Optimal trajectory planning.
Okay. Do you see the video?
I believe so.
Okay. So this is another use of this urban model.
And Jacques, if there is sound with the video, we don't hear the sound, but we see the video.
Okay. I'm sorry. Never know with the video. So I will try to stop here and comment a little. All you've seen here before is the way to apply those high resolution 3D models of cities. We started working on them for air quality, but then we realized that there were people quite interested in flying drones. So this video is the output of the current state of the art in a project called Descartes that we are doing with CNRS, the National Center for Research of France, and Create Singapore, which is a public-owned research entity in Singapore, which has an agreement with them, and the National Research Foundation, the NRF, in Singapore. And the objective is to apply numerical modeling in order to understand how you can fly drones for the delivery of urgent packages or organs, and how the drone delivery paradigm can be applied inside very packed cities. Like this area is La Défense district in Paris, but it's very similar to highly packed cities like Singapore, Hong Kong, and major cities in Asia. Understanding how the wind patterns develop is likely to help in poor air quality, which was the initial objective, but also for urban heat island effect, and as it happens here, for the drone delivery technology. I hope I've been clear enough. Then we may, if you want, we can skip here the end of that presentation on Descartes. I think we got the essence. I'm trying to go a little farther and to stop. So this is showing the drone moving into the no-fly zone and finding his way. Okay, I'm sorry that this cannot be seen as clearly, but if I send you to WeTransfer something, the complete presentation, maybe you can transfer it to our audience, Paolo.
Certainly. Anything you said that you want to share with the audience, send it to me and it will be provided.
No, thank you. I like
Send
the
that.
part about Jeddah, about Saudi Arabia. Really, it's good.
So I don't know whether you want me to stop now, because we have a time for discussions, which I think maybe also shared with other participants, or do you want me to go on with additional slides or not? That's
Well, first of all, thank you for the presentation. It's outstanding. I would like to ask the audience if there are any questions or comments.
No, thank you.
I don't have questions. However, thank you for the presentation. It's nice to see the simulations and how it actually occurs, and you see it after modeling.
The visualization is excellent. So Jacques, if you have if you want 5 more minutes to add additional slides, please go ahead.
there was time for 45, but I'll show you work done by our friends, our common friends of INET, that you know well, and they moved exactly as we did on the connection with the CAMS atmospheric, the Copernicus atmospheric monitoring service, and they have a system called Qualelaria in Italy since 2007, where they start from CAMS Global, which is the global system, exactly as we did for Saudi, but they made a full simulation for Europe. Here you can see the European map with maxima around downwind of London, and the Po Valley, and then you have the zoom over Italy. And they're running that operationally since many years now. It's a daily operational MET and air quality forecast. To do this, they have refined the farm multi-scale chemical transport model. And it's interesting to know that the farm is a flexible air quality regional model, multi-scale reactive. And it is initially derived from STEM, from the University of Iowa, the Greg Carmichael initial work. Probably remember Paolo.
Yeah.
And Giuseppe Calori was doing his PhD with Greg at the University of Iowa. And then they continued to cooperate. And Giuseppe and Camillo Silibello, they worked a lot, so that now farm is a very good tool. And the proof of that is that they have achieved a solution where they go down from continental, national, regional, down to urban scales with PMSS, of course. And in Italy, they have the national modeling system for the Ministry of Environment, that is ENEA mini system, and the regional EPAs. And the other places of application of farm are mostly done with ARIA technologies in France, because we work completely hand in hand. So there's a large number of applications. And you see here, the interesting point on this animation is the plumes from the volcanoes in the South Italy. It's fun. And a very impressive recognition for farm is the fact that if you look here, this is the CAMS ensemble modeling system. CAMS, the Copernicus Atmospheric Monitoring Service, is using the ensemble forecast paradigm. That is, they run in parallel 12 models at least. And among them, you have all the usual suspects. You have Chimère, the French one, the Danish one, EMAP from Norway, URAD from Germany, Lotos from the Netherlands, Match from Sweden, Mocage from France, another French guy, Monarch from Spain, the one from Baldassano former team, the Barcelona Supercomputing, Silam from Finland, and Mini, Italy, is farm. So actually, our Italian friends made it because Mini has been pushed by ENEA, by the national EPA in practice of Italy, into the club of models operationally used every day by the group of CAMS, the CAMS 50 service. I think it's a very impressive recognition. I'm happy for them, for Giuseppe, Camillo, and the whole team at Arianet, because it's a clear, impressive success. Now, since we were talking about Saudi, I've been putting also these this Kuwait air quality forecast system architecture. We made a work for the Kuwait Institute of Scientific Research and the Kuwait EPA. So it's always the same story, but with a different geometrical presentation. But we have emission inventories as input with geographic data. We have a MET input with WRF, and WRF is fed by GFS and the global MET forecast. And then we enter farm, and we have boundary conditions from CAMS on the bottom, and the farm air quality model. And we have a publication. I think this slide is the presentation of the nesting with a view that starts with Kuwait, a very little state in the middle, because they are in the middle of a very high emissions area. The Gulf is not the cleanest part of the world for emissions, of course. And here you have Kuwait, which I'm following with my mouse. And here you have the highest zoom we have for Kuwait. And it's operational since a year or so. And we have done also, INF has done the Northern Italy forecast for Lombardia region. They publish forecasts 3 days ahead. They do yearly air quality assessment over the region, scenarios, etc. And they also do same work for Lazio, for the Lazio Regional Environmental Agency, with nested domains. So I tend to be also always very happy to show what our Italian friends do, because it's a real win. We're a company with 2 heads in Italy and in France, and I like it. That's about all I had thought of showing. And if you have any question, I'm still available for a few minutes if needed. Otherwise, if you think I want to call it today, I will just make sure that I send to you the package with the data.
Very
And,
good. Thanks
just-
again, Jacques. This was outstanding. And I want to thank you for your time, and congratulations for all these international activities and the excellent visualization. The audio was not perfect sometimes. Maybe I didn't tell you it was up and down, but I think I heard what you were saying. And Paula Mirfat, how was your audio?
It's good. But I want to ask about you make the modeling on the Hajj season, that time in Mecca, Jeddah. It's traffic.
It's a very good question.
Crowded, yes.
It's a very good question, because at some time last year, but a little too late, we were asked by our customer at the National Center for Environmental Compliance if we could do some specific modeling for the Hajj, because there is a number of persons, cars, buses that converge to the city, which, of course, are changing very strongly the emissions pattern during the pilgrimage. And it would be very good or interesting to determining the impact on air quality, and which would be the ways to minimize this impact. Maybe just deciding that there's a fleet of buses that bring the pilgrims to the inner parts of Holy City without polluting too much. And it's a complicated story, but this year in 2023, we could not do anything because there was not time enough to put sensors. They wanted also to deploy sensors. There is a good possibility that NCEC is deciding to fund work this spring, that is ahead of the new pilgrimage next year. So we hope they will get the decision and the funding to help us doing simulations around the Hajj period.
Inshallah. Thank you so much.
Very good. So let's take a 10 minutes break and we will start again for the last seminar at 9:15 my time. Thank you again. Bye-bye.
Bye.
Okay, so we have about half an hour. I will give you a brief introduction to many other types of air pollution or atmospheric modeling topics that you should be aware of, and then go deeper if needed. You have seen an example of a Monte Carlo simulation done by Jacques a few minutes ago using Monte Carlo technique, all the dots. This is a very powerful methodology which I have used for many decades. I wrote many papers on these Monte Carlo techniques, and the idea of using Monte Carlo technique is to simulate air pollution by a series of fictitious moving points. So we call them particle, but they are not really particle. They are tracer. They are fictitious moving points. And this is an example of plume animation that I want to show you. I don't think I showed that to you before. Is something that I did almost 20 years ago. I've done many other animation similar to this one, which are better because our visualization technology has improved. But I work in projects that are confidential, and so I cannot show that to you. But this one is old enough that I can show it to you. This is an example of an accidental release of chlorine in a plant in Louisiana in the United States, and this is what I do in many cases, accident reconstructions for industrial clients and for litigation. So this is the plant in blue of the chlorine plant. We are very close to the Mississippi River, the biggest river in North America. And again, this is a 20 years old animation, but it's still showing the capabilities that we have with Monte Carlo techniques. We have a release location that is here. And I collected the meteorological data in the area. And then I estimated the emission rate. And then I ran my Monte Carlo particle model. And as you can see here, the emission is simulated with a clock here, minute by minute. The particles are moving according to the wind speed and wind direction. Let me restart. The particles are color-coded. Red is the highest concentration, close to the source. Blue is the lowest concentration, away. And as you can see, the industry was lucky in this case. The plume did not go to urban area on the left, on the right. The plume went straight down, remaining mostly confined in the industrial area. And in a couple of hours, the release is finished. So in this work, I was able to prove that, yes, we had a release. Yes, it was theoretically dangerous, potentially dangerous, but fortunately, the plume remained confined and did not really impact the urban areas. So there were no health damages in this particular area. If I have time at the end, I will show you some other example of project I work with, even though I have to be careful because, as I told you, they are all confidential. But the particle modeling or Monte Carlo modeling is quite powerful for accidents. Is not used very much for regulatory applications, but for accidental releases of 1 hour or a few days is excellent. And if you want to use a Monte Carlo model, I suggest you use the LAP model developed by my friends at the EnviroWare company. I work with them in all the time in all my projects. They are my associate in my business. And LAP mod is a model that they developed, and I was a co-author with them. And there are publication here in peer-reviewed literature that you can read about it, and there is a full user's guide, and you can download it and use it. Is free. And it is coupled, because we always couple air pollution and meteorological model. It is coupled with CalMet, which is one meteorological model developed by the US environmental protection agencies. So if you're interested in particle modeling and simulation of short-term, short-range emissions, LabMod is a very good way to start. I will send you a presentation I did in Italy a few months ago. I will send you a copy in case you're interested. Is a full presentation on Monte Carlo techniques in general. I think it's quite useful. Monte Carlo techniques can be applied to hundreds of applications, not just atmospheric diffusion. If you're interested in Monte Carlo, which is a very sophisticated technique, I will include my presentation in the material I will send you. What else can we say about modeling of air pollution? Well, in addition to diffusion, dispersion, chemistry, accident, we can also modeling adverse effects. Any type of adverse effects can be modeled as a post-processor. First, you run the air pollution model. Actually, first you run the meteorological model. Then you run the air pollution model. And then what is next? The effects. What are the adverse effects caused by the concentration that you simulated? So many times my client asks me not just to simulate air pollution, but to simulate the effects. And the adverse effects of air pollution are many. Of course, human health is the most important. Damage to animal and plants, damage to the visibility. For example, in national park, what's happening here? In national park, let me close and reopen. Sometimes PowerPoint is tricky. Okay, I will not click. Sometimes PowerPoint with Zoom is doing strange things. So I don't want to restart Zoom. They interfere with each other. Okay, now seems to work. So visibility in for example, in the United States, in national parks, we are very concerned about visibility. We want people to be able to visit the Grand Canyon and have a very big visibility of 40, 50, 60 miles without having haze, without having pollution. Agricultural production, sometimes air pollution may damage plants and fruits and vegetable. Property value. If you are near a bad area with air pollution, the property value of your home will decline. So all these things can be modeled. And we have algorithms and formulas and models to do that. The most important model, of course, is historically is the human health. And there are all sorts of numerical technique to calculate, for example, the risk of chronic and long-term health effect, the risk of cancer, the risk of other diseases. And I'm not going to show you all the formulas for health risk, but there is software designed to do that for you. For example, in the United States and in California, the HARP software is the most comprehensive. And this HARP software is doing everything for you. Is doing emission inventory, is doing air dispersion modeling, and is doing risk assessment for example, for cancer risk assessment. So if you're interested, here is the pointer with more information about the hotspot analysis and reporting program, which is the software HARP that I described a minute ago. This is very frequently used in California and also in other places. If you are interested not in doing the full risk assessment, but just in calculating cancer and non-cancer health risk, there is this site which is very useful. Is the Air Toxic Hotspot Program Risk Assessment Guideline prepared by the Office of Environmental and Health Hazard Assessment in California. California is always the most advanced state for everything related to environmental issues, air pollution, risk assessment. And so there is a lot of documentation and information that you will find in the California sites. I don't think I have the time to show you this, but yeah, I'll send you the slides. They are self-explanatory. You know, risk calculation are relatively simple, relatively linear formulas. And they are based on animal experiments, mostly. They are not based on actual examination of cancer frequency in humans. All these calculations are done by laboratory experiment of animals, and then they are translated to the to the human body. Other adverse effects on animals, on plant, on visibility. There is a section here of the EPA on visibility that you may be interested in examining, especially regional haze. That's what we don't want. We don't want to visit the Grand Canyon and see haze caused by sulfates, by air pollution. So there are a lot of regulations in the United States protecting visibility, and there are also visibility models that have been developed to calculate the amount of visibility impairment due to different levels of air pollution. One of these models is PluView. I don't know if I put it here in this summary, but yeah, there are models. There are EPA models that are calculating all these phenomena: the scattering of the sunlight, the light reflected, the contamination of light over the visual range. We want the sun is sending radiation over an image, and the image is reflecting some of this light to the observer, and we want the observer to be able to have a good view of the image without optical pollution. And there are, again, models and formulas that can help you understanding how much pollution can be tolerated if we want to protect the visibility in certain areas. Air pollution impacts on material, corrosion, air pollution impact on the work of art. For example, in Venice, Italy, marble and stones have been affected by air pollution. Here there is a pointer. Agricultural production, of course, air pollution may damage the agriculture. And let me show you one of the biggest projects I've done on agricultural damage. If you visit my consulting site, envirocomp.com, you will be able to see what I do as a consultant and some selected projects that are described here. Unfortunately, many of my projects, as I told you, are confidential, and so only a limited number of projects are described here. But the one I wanted to show you is this one. This was a big project in which in southern Idaho, DuPont and the government spray a oust, which is a herbicide. They spray this herbicide to kill the vegetation, to kill the bushes, and prevent future fires. However, unfortunately, after they sprayed this potent herbicide, we had dust storm. And typical dust storm in southern Idaho are wind from west to east. So I simulated the emission, transport, diffusion, and deposition of contaminated dust contaminated with oust. And I was able to show that we had 50 kilometers away, 20 kilometers away, even 100 kilometers away, we had substantial deposition of oust. And this created a lot of damage to agricultural products of farmers. So the farmers sued the government and Dow Chemical, and I was hired by the attorneys working with the farmers, and I was able to prove that the farmers were right. They were damaged by this oust material, oust dust, and I used the CalPAF model in this case, not air mode. I used CalPAF to simulate these effects. So this was a very successful project for me, for my client, and for the farmers. Since I'm here, well, now I closed it, but since I'm visiting my site, let me spend a few minutes. Again, you may have similar problems in the future, And so please contact me. I will be able to help you free of charge for a few hours, or as a consultant if you really need consulting help. Some of the projects I've done, for example, big fires. This was a big fire in Georgia, and I simulated a plume from the fire, and the part of the plume went up in the above the boundary layer, a few kilometers high, and was stuck there, and another fraction of the plume was impacting the area. I simulated a plume with CalPAF again, and I was able to make simulations that were quite consistent with the measurement. So again, this was a relatively successful project. A last one, I told you about chromium-6 in Iraq, which I simulated, and maybe the last one I want to show you was a big case, the Beverly Hills High School case. People claim that the area around Beverly Hills, California High School was contaminated by hydrocarbons over 50 years. And I was able to prove that that was not the case, that the emissions were relatively low, much lower in comparison with the normal traffic inside the area. We did an animation. Again, this is a 20-year-old animation. Now we do something much better in the current project we work. And this was in Los Angeles, a very contaminated area. So to claim that there was extra pollution due to this historic emission of hydrocarbon was quite absurd. This is a visualization of the downtown in Los Angeles in 3D, and then zooming in into the area of the Beverly Hills High School, where they claim that extraction wells caused air pollution of benzene for 50 years. So yes, there were extraction wells, there was some emission of benzene, but when you do the calculation, the comparison of this emission with the normal traffic in Los Angeles is negligible, absolutely negligible. So, okay, again, visit my site if you want to know more about our work. And of course, we will be available if you need help. My recommendation, if you start new project in your areas, is always to use some consultants to save time and start well. And then when you have your own team of expert and modeler, you can continue on your own. But at the beginning, it's very useful to have some expert to help you for a few months or a few years. Okay, so this is the end of the presentation number 2, and a few words on presentation number 3. A few words. I already told you about EPA models. You find them in the Scrum website of the EPA. You find all sorts of models that you can freely download, model well documented, well tested, and free. There are dispersion model, photochemical model, receptor model. I don't have time to talk about receptor modeling, but if you're interested, let me know, and perhaps I can send you some information. Other models ARIA, Jacques Musafir company, has a lot of models that you have seen today that are available. I don't think they are free, but again, you can use them. They have an excellent reputation. Also, EnviroWare, the company I work with in many of my projects, have their own modeling software, which I encourage you to examine. Many software may be useful to you, and they are free. And there are many research prototypes developed at universities around the world. Typically, they are free, but they are not well documented. So my recommendation is either the EPA or a reputable consulting company like ARIA or EnviroWare. A few words about odor modeling. I do odor modeling often in my project. Again, meteorological modeling, dispersion modeling, and then adverse effect. Odor is an adverse effect. And sometimes you need to simulate odor. Concentration is not enough. You want to know whether or not the population is being affected by bad odors. So there are chemicals like mercaptans or hydrogen sulfide, H2S, that are quite odorous. They are called odorants because they may create unpleasant feeling of unpleasant odors. Odor modeling is not easy, and there is a full chapter here that you will be able to access. This is part of my books that are available on the web, and this is a good introduction, this chapter on odor modeling and odor measurements. The problem with odor is that, number one, they are human sensation. They change from person to person. It's not like a concentration that you can measure and nobody can challenge you. You measure 34 ppb, part per billion, and it is what it is. Odor instead is a human sensation and can vary from one person to another. So that's the first challenge. The second challenge is odor is an instantaneous sensation. Most of our model, deal with hourly simulations, or maybe 10 minutes average simulations. Odor is instantaneous. So you have to address that. If you run the model for odor, don't forget, you need instantaneous concentration to understand whether or not you have an odor problem. So that's a further complication. I think that's all I can tell you right now. Again, if you're interested in acute case of exposure of air pollution, accident, visit my site, and that's my specialty. I do all sorts of air pollution modeling, but recently my specialty, half of my time is on accident, with some exception. For example, the Beverly Hills case I showed you a minute ago, that was a chronic exposure over 50 years. But again, most of my cases are accident, which is acute exposure. I have a presentation here in general on accident reconstruction and plume modeling. It will be in the document I will send you, and it will show more examples of the type of work I do, which is basically a post-accident investigation. I'm called after the accident to tell my client what happened, including the adverse effect and the damage. This was an interesting case of traffic collision. I've done a few cases of car accident, in which they blame visibility. They blame that there was limited visibility. That's why the accident happened. So they don't blame the speed, they don't blame the driver, they blame the visibility. So I have done several studies in which I calculate the air pollution present at the time of the accident, who created the air pollution, and how much visibility was impaired, to see if they have a point in blaming visibility instead of the driving skills. So again, these are litigation cases quite complex, in which I use air pollution modeling for special applications. My last slide is a series of pointers on topics that I don't have the time in this course to discuss very briefly. Inverse modeling. When do you have inverse modeling? When you know the concentration, you know the meteorology, and you want to calculate the emission. Normal modeling is you know the emission and the meteorology, and you want to calculate the concentration. Inverse model is the other way around. You have the concentration, and you want to know what and how much are the emissions that have caused that concentration. Inverse modeling. Litigation modeling, I told you a few things about it. Indoor modeling, I've done some indoor modeling, very important, especially for COVID. You need to use grid models, especially CFD, computational fluid dynamics model. COVID modeling, again, I have the pointer here. Emergency preparedness and response, very important. Is easy to try to be prepared. It's very difficult to have a response in air pollution. Pesticide application, I told you something. There is a pointer here. Visibility modeling, we discussed a few things. Receptor modeling, we didn't have the time, so I will let you read about it if you're interested. Landfill modeling, we didn't talk about it, but emission from landfill, emission of methane, emission of hydrogen sulfide are very important. If you both for local studies and for global studies. And finally, fire plume modeling. Yes, we had a full seminar by Dr. Friedman on fire plume modeling. Very good. So I hope I didn't go too fast. I hope everything was clear. I have a question about the sound quality. During the presentation by Dr. Musafir, the sound quality was not perfect. How was the sound quality of my voice?
It was clear, even during his presentation was clear. Maybe it was only on yours. I'm not in me, but was clear. But in mine it was.
What was worse?
It was.
Okay. Because I had problem with the quality of the sound of Dr. Musafir, but it was only me or also you?
In mine was clear.
Very good. Very good. So it must have been my headphones. I use always the headphone because I think they are the best, but sometimes apparently don't work perfectly. I just wanted to check with you. Okay, so again, give me a feedback by email or call me or whatever you want. I'm always open to suggestion. I try to give this course once a year, and it's impossible to cover everything, but I try to give an introduction to everything. So let me know if you enjoyed it and if you have suggestions for the future. We have a few minutes for question or comments if you want.
Thank you so much.
Very good.
The presentation is really good. I feel proud to take this short course. I like it. Everything, every topic is good for me.
Very good. Thank you. And I will continue with this formula. In the past, I used to do it only by myself, losing my voice at the end of the third day completely. But now I've used the guest speaker, and I think is a good formula for the future to have a basic course with the 3-4 guest speaker. I will continue with this formula in the future.
Great. Thank you so much, Paolo. It was a very complete course. Maybe a suggestion I have is would be nice if you can include a practical session, kind of to input data in a modeling, I don't know, all those that you mentioned, the kind of modeling that you have. So it would be good for practical lesson.
Yes, in the past, sometimes I spent half an hour playing with screen view and showing some examples of using the screen view model to simulate a plume. So I'll next time I will dedicate half an hour for that. I thought Jesse was supposed to do that during this course. That's why I didn't do it. But Jesse did something, but it was very quick, only 5-10 minutes. So I was expecting him to do it, but he didn't do it. So next time I will do it. This course, there are specific courses. I want you to be aware of that. If you are interested in courses that teach you how to use a specific software, for example, air mod courses. You see, for example, Lakes Environmental and Trinity Consultants are the two main companies that give courses on specific software. For example, Lakes software, upcoming courses. You see, they have courses on AirMod and CalPAF. These are courses specifically doing example and test using this software. And Trinity also, let me show you. Trinity Consultant also give, here we are. They do courses for $1,000 in different cities all over the world. And I'm sure they do it online to show their software, Breeze, they call it. And is basically air mode. So that's why I don't do it. I do a general introduction because there are other courses that will cover that, and you may want to attend them. They are quite well done by both companies. But again, thank you for the comment. In the future, I will add maybe half an hour of playing with screen view. And remember, tomorrow, download screen view and start playing.
Thank you so much, Paolo.
Very good. Goodbye, and let's keep in touch.
Yes, goodbye and have a good day.
Bye.
You too. Thank you. Excuse me, Paolo.
Yeah.
We will receive this course, the recording of this course.
Oh, okay. The material will be sent to you like I did yesterday with Hightail. The
Okay.
video need to be processed, and then
Mm.
they will be inserted. The video will be inserted in APSI,
Mm.
in the matrix. So in a week or two, and I will let you know, a lecture set. You see, there is a lecture set here in APSI with the videos of my course in 2022 and 2021. So these
Mm.
are already available, but
Mm.
the 2023 will be added here to the lecture set, and you and everybody else will be able to access the full video.
Okay, thank you so much again.
Very good. Bye-bye, and thanks again.